relations and functions. So a relation, any set of ordered pairs that are related. So if you think about it, if you can write an equation for it, it's a relation. It's a relation, because there's a relationship straight away. Parabola, y equals x squared. Hyperbola, y equals 1 on x. Cubic, y equals x cubed. Circle, x squared plus y squared equals the radius squared. There exists a relationship between the x and the y value. So they are relations. So, there's an example, x squared plus y squared, 25. A function is a very special type of relation. And it's one where the x and the y values have what's called a one-to-one relationship. Okay? So for every x value, there's a maximum of one y value. Now there might be none, such as like with the hyperbola there, at x equals 0, there does not exist a y value. That's fine. A maximum of one value. And that's what we call a function. So y equals x squared, our parabola, that would be a function. Doesn't matter which x value you pick, there's only one y value you could read off that graph. Visually, an easy way to tell is what we call a straight line test. And that straight line, of course, is vertical. But if you were to imagine sliding a vertical line across the graph, if it hits it only once, then fine, it's a function. But as soon as that straight line hits the curve twice or more, no good. So a straight line drawn parallel to the y-axis, so vertical, it'll cross it once, if at all. So if we look at our four graphs there, parabola, that's fine. Hyperbola, yeah, once, none, that's fine. None. Cubic, that's fine. Circle, it's okay. Then I hit the circumference and I'm a tangent, that's okay. But as soon as I go past that tangent, no good. Hits the circle twice. So the circle would just be a relation. It wouldn't be a function. So there we go. Hyperbola, doesn't matter where I put that line in. Once, if at all. So very good. Tick. Parabola on its side, x equals y squared. Again, I could start out, everything's fine, but once I get past that y-axis, no good, hits it twice. So, no. So, that's a visual way of doing it. Relations are usually made up of several functions joined together. So you can break a relation up and say, oh, well, it's this function and this function. And usually the way we do it is things like this. We say, oh, well, we could have the positive square root. Because if I was to make y the subject here, I'd get plus or minus the square root of x. If I was to just draw y equals the square root of x, I'd get the top half of the parabola. If I was to draw y equals minus the square root of x, I'd get the bottom half of the parabola. So it's those two functions joined together. I didn't mention it there. I thought I did, but I'll mention it now then, whilst it's not written there. Algebraically, the way you would check to see whether it is if you were to make x the subject, is it unique? So with y equals 1 on x, if I was to make x the subject, I'd get x equals 1 on y. That's unique. Whereas with x equals y squared, I get y equals plus or minus. Two possibilities. Not unique. So I suppose algebraically that's the way I could tell. Only one possible solution. So as soon as I go plus or minus, two possible solutions. Visually, of course, that's why it's great. If you know what basic graphs look like, fantastic. Because it's just a lot easier to look at the picture and go, oh yeah, that one's a function, that one's not a function. Domain and range of y equals f of x. And I guess the main reason we use f most of the time is function. It doesn't necessarily mean this is a function, it could be a relation, but we use f a lot. Domain, every possible value of x that you can substitute into fx, so into the function or relation, whatever it happens to be. You could think of like function x as like some sort of data machine. So input is what you're feeding into it. So domain is what you're allowed to feed into it. So it's the input of that function relation. So if you want to find a domain, we look for values, we actually look for things that can't happen. Right? Because if you look for things that can happen, you'll be there forever. It's usually easier to look for things that can't happen. So here's x equals y squared. Again, visually, great. If I've got the picture, I can see it. Because I can just imagine, you're walking along the x-axis as you do. Look above you, look below you, and see if there's any curve there. And so I'd start along here and go along the x-axis and go, nah, can't see anything. No good. Nah. Well, I get to the origin. What's this? Something starting. Oh, wonder what happens. And you keep going and you go, whoa. Oh yeah, look at this. Look at this parabola above me. So once I get past 0, it always exists. So my domain here would be x is greater than or equal to 0. I can substitute any number greater than or equal to 0 and I'll come up with an answer that will exist on our curve. These sort of split functions, sometimes called step functions, also known as piecewise functions. There's all sorts of wonderful names we give these things. So the domain for this one would be x is less than or equal to, because it's coloured in, 0, and x is greater than 2. So if you've got to find the domain, you don't know what the picture looks like. So let's say, if you know what the picture looks like, it makes life a lot easier. You can just look at it and go, oh yeah, okay, that's the domain. If you don't, the sorts of common things that arise. Fractions. There's a key thing we know about fractions, and that is the bottom of the fraction can't equal 0. You can't divide by 0. So if you've got a fraction, have a look at the bottom of the fraction and say, well, is there anything here that would make this equal to 0? In which case it won't be in the domain, because you can't be 0. So for example, there's that classic one, y equals 1 on x, our hyperbola. We look at the bottom of the fraction and go, oh, hang on, bottom of the fraction can't equal 0. So I know x can't equal 0. Now that's not the domain. Don't ever write that down as the domain, because the domain is a set of points that are included, not a set of points that are excluded. So if you write down x is not equal 0 for the domain, we'll go, okay, that's fine, x can't equal 0, but what can it be? You're not telling me what the domain is. So you would write down something like this: all real x except x equals 0. Now, grammar, it's a wonderful thing. The English language is weird. Of course, depending on how you say this, whether you'd write an equal sign or a not equal sign. Because you could say, well, I've got all real x, except x equals 0. I don't have it. Or you might say, hey, it's all real x, except x can't equal 0. So, which do you put down? I don't think it's really a big deal. You're sort of making a point that, hey, 0 is not part of this domain. Oh, and it's important you put all real x. If you just write all reals, you're not telling me you understand that domain is the x values rather than the y values. All right, 1 on x squared minus 1, bottom of the fraction can't equal 0. X squared can't equal 1, so x can't be plus or minus 1 in this case. So domain, or real x, except x is plus or minus 1. Can't have those values. You might have two fractions. The rules are still the same for both fractions. So x minus 1 can't equal 0. And 7 minus x can't equal 0. Giving us our 2 points of exclusion for this curve. So all real x except x equals 1 or 7. Okay, root signs. Or I suppose, more importantly, even root signs. Because you can't find the even root of a negative number. You can find the odd root, like cube root's fine. And square root, of course, is the most common one we're going to come up with. So you can't find the square root of a negative number. So if I have something like this, square root of 4 minus x squared, by the way, what does it look like? Do we know? Half triangle. Ooh, close. Yeah, half a circle. Semicircle. So say, if you recognise it, fantastic, you can get the domain real easy. Mental blank, don't know what it looks like. But what I do know is whatever is under the square root sign has to be greater than or equal to 0. So 4 minus x squared has to be greater than or equal to 0. X squared must be less than or equal to 4, which means x ends up being in between minus 2 and 2. There's my domain. And if you think about the semicircle, yeah, that makes sense. Between minus 2 and 2. I've got two square root signs. Again, the rule's the same for both. X plus 3 must be greater than or equal to 0, giving me x is greater than negative 3. 5 minus x is greater than or equal to 0, giving me x is less than 5. Both have to be true, because I have to be able to substitute into both of those things. So I end up with x being in between minus 3 and 5 for the domain. Combine the two together. Fraction with a square root sign on the bottom. So we'd say what's under the square root sign has to be greater than or equal to 0. However, it's on the bottom of the fraction, so it can't equal 0. So it'll just be x plus 2 is greater than 0. So in this case, x is greater than negative 2 for the domain. Right, let's talk about range. Range then is the answers. Once we substitute in every possible point in a domain, what are all the answers that we can get? So it's like the output of our machine. What comes out of this thing? Visually, once again, now we're doing a little bit of rock climbing, or if you prefer to go down, abseiling. Where's the curve? Well, no matter where we go on this one, it's everywhere. So all real y, every possible number we could get as an answer for that one. With our step function over there, we get answers that are less than or equal to 1. We also get answers that are bigger than 3. Don't know what the picture looks like? What to watch out for? Things that are going to give me maximum or minimum values. And that's usually things like squares and absolute values, things like that. So even powers, absolute values are always positive. So that might create a biggest it could ever be or a smallest it could ever be. So y equals x squared, the classic parabola. Well, the range is going to be greater than or equal to 0 because that square always has to be positive or 0. And they're my answers. All right, so x squared plus 3. Well, I know the x squared is always greater than or equal to 0. So therefore y must be greater than or equal to 0 plus 3. So I'll only get answers that are bigger than 3 for that one. 5 minus x squared. The biggest x squared could ever be is 0. Because now it's negative. Always going to be a negative number. So y will always be less than, in this case, less than or equal to 5 minus 0, 5. And similar with absolute values. I mean, absolute values always have to be positive. So y is greater than or equal to 0. Yeah, okay, so the absolute value has to be positive. So that has to be greater than or equal to 0 minus 5. So we get negative 5. Restrictions on the domain. So we've looked at our domain and we've found that no, it's not all real x. There are restrictions on it. So, so many of these things turn out to be symmetric. So a good idea is substitute in the endpoints of the domain, see where it starts and finishes, and then have a look at the middle as well. The vast majority of times that's going to cover your domain, cover your range. So there's 4 minus x squared. We discovered it had a domain of minus 2 and 2. So I'll substitute in 2, I get an answer of 0. I'm not going to worry about subbing in negative 2 because I'm squaring, obviously I'm going to get the same answer. Substitute in the middle, I get 2. So there's a good chance that this is going between 0 and 2. And if you think of your semicircle, yeah, it does. It goes between 0 and 2, the range. Fractions. If you have a constant number on the top of the fraction can't equal 0. You cannot divide a number by something and get nothing. Impossible. Cannot be done. So y equals 1 on x. This fraction cannot equal 0. So y can't equal 0. But again, that's not the range. The range is what's included, not what's excluded. So it's all real y except y equals 0. 5 plus 1 on x, the fraction can't equal 0. So therefore y can't equal 5 plus 0. There's my range. Ooh, x plus 7 is not a constant on the top. But I could rewrite that fraction. It's actually 1 plus 3 on x plus 4. fraction has a constant on top. And if, by the way, if you didn't realise that straight away, you could do a quick little polynomial division over on the side. X plus 4 and x plus 7. That goes once. Remainder 3. So that's where we get our 3 from. Okay, y can't equal 1 plus 0. So there's our range, all real y, except y is equal to 1. A little bit on notation here. Function x, well, fx I should say, because it could be a relation. In this case it's not. 3x squared plus 4. It basically just means substitute in 5 for x. Everywhere you see an x, put a 5. Oh, 3 5 squared plus 4, 79. But doesn't have to be a number, could be another pronumeral. Function a. Everywhere you see an x, put an a. Oh, 3a squared plus 4. Doesn't have to be one pronumeral. Function x plus h minus function x, which will become a really common one that we'll do later on. Okay, so function x plus h will be 3 lots of x plus h squared plus 4 minus function x, which is 3x squared plus 4. Expand out, collect like terms, there we go, 6xh plus 3h squared. All right, 2f.